Thank you. I guess it's both for Anna and Thomas then. So I'm curious with the 422 date in Apollo 16 samples. So these samples you said were noretic, anorthotic stuff. Are they? Do you interpret these samples as crystalline impact melts that form during the serenitatis impact, or are your zircon ages reset by the impact?
In the samples that I presented, there is no impact melt. They're cataclastic, entirely deformed. So these are resetting ages.
On the one I presented, it's believed to be a cumulate from a creep ridge melt. So it would have crystallized as a melt rock from the creep ridge melt formed during serenitatis and then likely transported to Apollo 16 with the embryo ejector.
Thank you. I guess just following on from Roma's question really as well, because I guess, so Tom, some of the samples that you presented are also got granulitic components as well. And I guess also then throwing it to Anna slightly too, what my thought was, can you rule out the fact that these 4.2 ages could reflect crystallization ages of MG sweet material?
Those two that I showed here are not grouped in the MG suite. There is some relation there.
But I guess the protoliths of some of the granulitic components are potentially linked to MG suite material. So there might be a component in some of these rocks.
Yes, but the crystallization that we're dating here is either crystallization from the impact melt for 67955, and for 77017, it is either from an impact melt or recrystallization when it was deposited in a hot ejector unit. That's, I don't know, for Anna's.
Yeah, so again, in these cases, we don't see any evidence of crystallization there. We didn't really study the structure because they're so tiny. They're in some cases 5 microns. So we compare with the vast literature where they did study the structure. But in the case of Apollo 17 shocked norite, the 4.22 is again the formation age, and the 4.33 is crystallization age that we believe then crystallized again from the impact melt. Crystallization, but from the impact melt.
Cool.
For the older age.
Yeah, no, thank you. But there's some interesting things in terms of the trace elements of those rocks. I'll be keen to chat to both of you afterwards.
Jackie Clark, ASU. Fiona. I forget what the linear features are called and the merilites. What are they called?
I don't know yet because
Okay.
I haven't seen them before. So I saw them like either fractures or lamellae.
So off the top of your head, comparing the various merlite grains, do you see like preferred orientations that are similar, comparable to all the other grains, or are they just completely random to the individual grains?
It looks similar, but I still have to look into the details. They follow some kind of the crystal letters or anything here. They follow any.
Yeah, I mean, that's my recommendation,
yes,
just to like
exactly,
map them
yeah.
out.
Thank you.
I also have a kind of a question, or maybe just something to think about for Fiona, is that, I mean, you're talking about the samples that were excavated by Cone Crater, because that came from just close to the rim, being slightly older. And have you considered that maybe they were just buried in the ejecta blanket and didn't close as early as the samples that were selected from the surface, though there by the landing site? Could that account for this 10 million year difference, so that you don't have 2 impact events, but just a closure, a temperature gradient?
Yeah. I mean,
Like,
that's why I want to do also the ion imaging. We have to do some diffusion modeling because it depends, of course, on the grain size and on the temperature they've experienced. But under the ejector blanket, I would think they will experience longer, higher temperatures, maybe have more time for lead diffusion. But yeah.
So I was just reminded that we must be out of here at 7 o'clock, but this is just so interesting, so discussion. So we can continue afterwards. But two things I just wanted to point out. One is that it is amazing that now we are talking about all the ages in Apollo samples that are actually older than 3.9. So that is quite a big pivot that, you know, regularly we are finding ages which are 4.2, 4.3, you know, of that range. And secondly, Thomas, in your data set, you tried to link tritium with one of those two ages that you were showing. My understanding is that tritium material is very low TI basalt. 70017 isn't. Or do you have any indication? I mean, that is very creep poor, anything tritium wise. So how can you relate that to any of these samples?
Low titanium basalt. You mean tritium, like to fill in? Now, what we're thinking we're having here is material that got molten during the impact event and then ejected, and the low titanium basalt would have come in later, right, to fill the cavity. So this is a later event.
So is the crustal material that you are thinking of being ejected from tritium?
Yes, and then either recrystallized or molten and then crystallized, likely as a external melt, like that got ejected during the tritium event, or potentially Magnetars.
Yeah, I mean, the only thing I would have thought that if that basement through which the tritium has come, if it was creepy, then that would be reflected in the tritium material as interaction of that material. We don't see that, but maybe we don't know enough about.
Yeah, but that again, the material that came from below that filled the cavity, that was after the basin.
I know, but that's what I'm saying. But there must have been some interaction with that material when the tritium melt is coming up, you see, because it's coming through that same basement. Is that not? No, maybe we can continue.
Yeah, maybe we
something
can
there.
Talk about that afterwards.
I just want to comment to Fiona. I mean, to me, those features in Merlite, they just look like they were following cleavages in Merlite. So whatever is happening, it is crystal structure controlled. So we must be able to pin it down. I mean, you are going around the right route. Only thing I can suggest is perhaps there is a potential for something higher resolution atom probe type thing that you might want to consider looking into.
Yes.
But again, lots of discussion, but thank you very much. I think Katie has got a final word. So here we go. After Katie, we will go to social dinner.
So there's a lot of confusion about Chrysium, Serenitatis, Nectaris. Where do we persuade ESA to send one of their EL3 missions to? Right, so we want to date one of those basins to calibrate the ancient impact chronology. I think that's the most important scientific question we as a community can get behind to look at the bombardment history. So where do we go? So Chang'e is going to sample SPA. If we rule that out, where do we want to go to calibrate? Which impact melts do we go to?
For me, or who should answer? Okay. For me, short answer, if you want to do Chrysium, go closer to it, because with those craters that we looked at, when we looked at the melt distribution from Tiantian's models, it's the closer you get there, the less of, obviously you get Serenitatis, the more you have Chrysium. I mean, it's obviously just spatial relationship, but the modeling of the melt distribution shows that as well. So if you go closer to crater rim, you probably find more samples.